Hi folks, this is Nicolas Frankel. I'm a developer advocate at Hazelcast, and at the Big Data Conference Europe 2020, I will have a talk about introduction to data streaming. In this talk, I will present you first the batch model, how it came to be, its use cases, and of course its limitation. And then I will introduce data streaming and how it can overcome those limitations, how it can also let you do stuff that you couldn't do before. And at the end of the talk, I will have what I hope will be a cool demo where I will present you an app where you can see the location of all public transportation in Switzerland in near real time, thanks to data streaming and Hazelcast. So here is it. I hope you like it, and see you at the Big Data Conference Europe 2020. Hi folks, thanks to be here for this talk about an introduction to stream processing. I'm Nicolas Frankel. I've been working a lot in technical roles, developer and team lead and whatever, and since 2 years, I'm a developer advocate. I work for a company called Hazelcast. Hazelcast has 2 products. The first one is an in-memory data grid, and if you have never used an in-memory data grid, you can think about it as distributed data structures. So instead of having a map inside your JVM, then you can shard it and replicate it all over the network. And the other one is Hazelcast Jet, and since I will be using it in the demo afterwards, I won't delve further. This is our agenda for today. The first point is, right now, you might have heard a lot about streaming, stream processing, data streaming, this kind of stuff. So I would like you to tell you about why we are at this point, the different streaming approaches there are on the market, a bit about Hazelcast Jets, and after streaming we will need to have some data. So I would like to just a few words about open data, that the data that you can use already to create cool stuff. And the demo at the end will be about showing all the public transportation in Switzerland on a map. So I will need to have a standard for that. So I will talk a bit about the general transit feed specification. And afterwards, if I have enough time and if the gods of the demo are with us and with me in particular, I will try to show you the demo. So when I started working 20 years ago, a long time ago for most of you, well, every single piece of data was stored in SQL databases. There was no choice. You wanted to store something persistently, you had to use the SQL database. And even at the time, SQL databases, there were use cases where it was not that great to have a SQL databases. I can think of 2 examples. The first one is analytics. Imagine you're the director of a supermarket and you probably want to have the sales of the previous hour. And then perhaps you know that you have a lot of bananas in stock and you didn't sell enough banana and you need to sell them today. Then probably you will check the sales of the bananas in the last hour, and you can check that if you will have stock left at the end of the day, then probably it's time for a discount so you can sell every banana in your stock. And the other use case where SQL databases are not that good is reporting. Probably you are in the bank, you have a bank account, and you receive every year or every month you receive your report, your balance. And for those 2 use cases, SQL databases were not really adapted. And the reason for that is in the analytics and the reporting context, we do a lot of reads. We only do reads. And SQL is very good, very well adapted when you are doing both reads and writes. And for that reason, SQL has like normalized data. You must respect the 3 normal forms, so you don't duplicate data, this kind of thing. When you are reading, that means on the other side that if you don't duplicate data, probably you need to do joins across several tables. And the more tables, the more joins, and the more joins, the worse the performance. And again, for analytics or for reporting, you want everything right away. So there is the tension between, like, on one side, I want to have data normalized, and on the other side, I want to have data denormalized. And it boils down to, when you write, you want the data you write to be correct, but when you read, you want to be very, very fast. And as I mentioned, with SQL, you have no choice. You probably have a database administrator that forces you to have normal forms, and then you have joins, and probably in order to have the correct data, you have constraints on the types, on the primary keys, and everything like that. And well, we have different people who have different use cases, and so using the same database doesn't make much sense. So even if you are only using SQL databases, and remember at the time we were only using SQL databases, there were talks about like object-oriented databases, but I've never seen them in the industry. We had a batch that read the data from like the transactional database, that transformed it in a way that would be easily consumable by like the analytics or the reporting software, and put it into a denormalized database. And that was probably called your data warehouse. That's what we are doing. That's what we were doing, but probably you are still doing it, because batches are everywhere. Like in 20 years, I went to a lot of different customers, and I always saw at least one, and of course, many more batches. That's the way to go. That we have this legacy of batches, and they are everywhere. And there is this fun like properties of batch jobs. The first thing is they are really good. They are scheduled. There might be batches that are launched manually, but most of the time they are scheduled, and they run into a specific amount of time. And of course, they should run in a time frame that is less than their interval. That's generally what you check when you start developing the batch. If you have an hourly batch, it should run in less than 1 hour. And at the beginning, that's a given. You actually like you develop your batch in such a way. But the fun stuff is probably your data will grow over time, and you will see the time it takes to run your batch increase over time. And I believe you've run into such issues that at some point, the time it takes to run the batch overlaps the next execution schedule. It might also happen that the batch runs until like a certain point, fails, and you need to restart it. And it makes the time it takes to run the batch even larger, and you run the risk you have even higher risk to overrun the next execution schedule. You might also like exceed the data storage, whether it's on disk or on memory. I mean, there are a lot of interesting challenge to batches. So regarding the fact that it fails in the mid execution, well, you can decide to only like chunks of data and commit after each chunks. Also, it keeps the memory issues like in check, because you don't need to load the whole data in memory, but only the chunk. But then you open another kind of worm, because what about if meanwhile there is new data coming in? And actually, it wasn't feasible anymore. We were hitting the limits of the hardware. We were hitting the limits of the vertical scaling, because all those SQL databases, they were very nice, but they were designed at a time where the load of data to handle was acceptable, and you can run only on one machine. And most SQL databases, the legacy one, they run in the leader-follower mode. So if you have a cluster, only one node does everything, and then if there is an issue, there is a failover to the follower nodes, which becomes the next leader. But actually, it's still one machine doing all the job. But with data becoming ubiquitous, when like analysts wanting more data, business wants more data all the time, we needed a way to scale horizontally, and SQL databases were not made for that. So there was this first initiative about MapReduce, and MapReduce is actually like by design made to scale horizontally. And then with MapReduce came the whole NoSQL like databases, and they had interesting views. Most of the time it was, we can remove constraints, we can remove joins. The idea was to write and read very fast, and that schemas were not that great when you wanted to do that fast. We can argue whether it's always a good idea, because if you don't have a schema when you write the data, when you allow everything to be dumped into the database, then probably when you read the data, you need to have like some sort of validation. And then when you do like very, very fast writes, then the reads is becoming slower. But again, it depends on the use case. But actually, right now we have another way of looking at things. And this way is everything can be an event. And events are actually a thing like can be traced back to like graphical user interface. Because when you develop a GUI, when the user click on the button, then it generates an event, and you subscribe and you say, oh, I will handle this event. And the idea is, okay, but when something is generated, a piece of data is generated, it can be modeled as an event, and we can react on that as well. So the idea is, instead of having those batches that starts at a specific point in time, they are scheduled, that make everything event-based. That's a good idea, actually, because then it entails a lot of benefits. The first is it's very memory friendly, because instead of having the whole data to load in memory, then you can have only the single piece of data that is modeled as an event, and that is much, much smaller. And for the same reason, it's easily processed. The other benefit, that is a nice side effect, is that instead of having to gate the data every time we need it, then the data is pushed to us. And in that way, we are much, much closer to real time than before. You don't need to wait the hour or the day batch to get the data. And so that the data that you get is like, can be considered derived data, and it's like close to real time regarding synchronization. There is a new thing also, is when you consider a batch, you take a finite data set. You take what's in the database. But when you start doing data streaming, then it never ends. You know when it starts, but you don't know where it ends. So if you have been working in whatever language, I'm a Java developer, for example, with like Java streams can be infinite. And it's really strange when you start working from collection and then you end with streams, because you must always think that, hey, it might never end. And that's exactly the case. Streams in general, like events, are processed individually, and that's a good thing. They are stateless, but sometimes you might want to do aggregation because you want to have like statistics all the time. Like, as I mentioned, you want to have the sales in the previous hour. Then probably you will need to like aggregate the state over several events, and it's possible. They are called stateful streams. And in that case, you need to consider the interval, but the interval is not as previously as what are the sales in the last hour, because when you've got a stream of uninterrupted events, then you can have windows, but the windows, they can be tumbling like every hour, like starting at 9 and 10 and 11, or they can be sliding windows. Or sometimes it's not, they might not be even regular. So sometimes, for example, for web sessions, they can be bursting. So for some time, there will be a lot of events regarding a specific session, and afterward it will end. And the stream must understand that, all those events, they belong to the same session. So there are other interesting concepts to think about. But when we think about streaming, actually, it's just as before, it's extract, transform, load, but in a very smart way. Of course, we have a lot more data sources as sources and a lot more data targets as targets. But as I mentioned, the idea between doing stream processing is we can scale horizontally, so you can distribute your load all over the network. You probably also want to do some enrichment at some time. As I mentioned, the events in general is as small as possible because you want it to fit into memory. So you might not have the whole data available. And probably you have the ID, for example, of a sensor, but you want in the final target to have the whole sensor data. So you need to enrich your events with the whole sensor data, which is stored somewhere. And in the regular ETL, if you want to do this kind of stuff with SQL database, you probably need to add an additional join when you are doing the ETL, perhaps from another database. And again, this slows down the batch. With like stream processing, the usual way to do that is to load everything into memory. And of course, it consumes a lot of RAM. But then the enrichment process can be done very, very fast. And it opens a lot of new possibilities. As I mentioned, we are very close to real time now. So you can have dashboards that reflects the reality, minus the processing time, of course. ML, machine learning, is very hype right now. So imagine that when you receive your stream of events, you can apply some machine learning model on it, and then you can predict what can happen. 10 or 15 years ago, there was this like enterprise service bus in the enterprise. They were pretty popular. They were kind of like the embryo of stream processing. And the idea was when you produced events, then you would dump them into the enterprise service bus, and then there would be some components listening to them and trying to make something out of them. And the idea was, if you could aggregate several different events coming from different pieces of software, then you would be able to infer some higher level logic. And this was called complex event processing. For whatever reason, I never saw any CEP in the wild. Like, it was in the books, but I never saw any. There might be companies that did it, but it was not in my experience. But now with stream processing, you can really have complex event processing. Like, you can have a monitoring system that says, hey, like I'm checking the state of, I don't know, like the price of rice, and if it drops 2 times in the latest 2 minutes, then I will probably need to sell my rice, or this kind of stuff. Now, when we talk about events, probably you will need to store them. And right now, Kafka is the king of events storage system. You might also check about Pulsar. It has a slightly different architecture, and some people are thinking that Pulsar might also be a good thing. And the good thing about Kafka, it's adapted to those modern architecture. So basically, it's distributed by default. And when you write a message, you write a message to a topic, then the topic is the abstraction you use, but basically the underlying architecture makes it distributed. And of course, it's stored on disk. And now, when we have our events, we can process them. And there are a lot of stream processing engines on the market. Of course, there is Hazelcast Jet, but there are also Apache Flink on-premise, on the clouds. I mean, every cloud provider has its own stream processing engine. I just need also to mention Apache Beam, because Apache Beam tries to be like an abstraction over some of the above. And so the idea is, just as any abstraction layer, you would just only use the regular API, and then you can like remove one of the stream processing engine and put it on another. It's a bit harder than that, of course, because there is no standard regarding stream processing engines. And so it's a leaky abstraction, but it's still a nice effort toward making it like more standardized. And yeah, a few words about Hazelcast Jet. So it's an Apache 2 license open source project. Underneath, we are using the Hazelcast IMDG, so the distribution is based on IMDG. And if you're coming from a batch background, it's nice because you can start with standard batching, and then with one line of code, you can go into the realm of streaming. And of course, we have like an enterprise offering, but everything that I show you in this demonstration afterwards is completely open source. Hazelcast Jet defines two concepts. You will find those two concepts probably in all stream processing engines, perhaps under different names, but the concepts they stay the same. So first, when you develop your codes at coding time, then you write your code. You will say, I will read from this source, I will do those steps, and then I will write into this sink. And this is the pipeline, and then you use the Jet API. And then you will have a client that will send this code to the stream processing engine. And it's the job of the stream processing engine to execute it. And the stream processing engine knows about the topology. It knows how many nodes are in the cluster. And it will run this pipeline on the cluster, and then it becomes a job. Jet has two deployment modes. If you are a Java developer, and the easiest way to start with is with the embedded mode. In the embedded modes, Jet is just jar that you use as a dependency. And when you've got it in your dependency, you can create a new Jet node with jet.newJet instance. By default, Jet will multicast over the network, find other Jet nodes, and they will form a cluster. This is very, very easy to start with if you are a Java developer. But there are two issues with that. The first issue is once you hit the limits and you want to scale horizontally, well, you will need to scale your cluster along with your application. So depending on which limit you hit first, you will both need to scale horizontally along the Java application with the Jet cluster. The second issue is if you want to configure your JVM according to a workload, probably the workload of Jet is different from the workload from the Java application. So it will be quite hard to fine-tune the JVM. So if this context fits you, there is no reason to change it, but perhaps at some point you will hit the limits that I mentioned, and you will need to change it to another deployment model, which is the client-server model. Client-server model decouples entirely your Jet cluster from your application. And so you can configure the JVM accordingly, and you can scale your application nodes and your Jet nodes independently. There is another side effect that is beneficial, is the embedded mode is very good for Java developers. But if you're using the client-server mode, we have a lot of different language stacks that you can use with. So for example, you can use Node.js, you can use C#, you can use Python, you can use Go, you can use C and C++. In that case, in order to connect to a Jet cluster, it's a bit different. And this is the bird's eye view from Hazelcast Jet. By default, we have a lot of different connectors, so from sources and to targets. And the good thing is, if something is not available, for example, you want to read data from a web service, then you have an API that allows you to do that. And as I mentioned, Hazelcast Jet is a stream processing engine. So this is just the implementation of the schema I showed you before. It's very well integrated with IMDG. The use case that I mentioned before, the fact that, hey, you want to preload everything into memory, well, you can preload everything from like your reference table into Hazelcast IMDG. And because we leverage Hazelcast IMDG inside, then we can like enrich the data like much, much faster. Now we have stream processing defined, and we want to do some cool stuff with it. We need data. And of course, I believe you have a lot of data available inside your company, but I want to show you a demo. So I want to have data that is publicly available. So I just want to talk a bit about open data for the moment. And yeah, open data is to data, is what to open source is to software. It's the idea that, yeah, it's cool to have data that is like freely available, that you don't need to pay for, that there are no rights to use it or whatever. And of course, it's general, it's backed by government and administrations. I'm from Europe, so I know about different initiatives in France, Switzerland, and the European Union. Here are the links if you want to check them. But I've seen, for example, that California also has some open data initiatives, so you must check regarding your own country. Now it's just the beginning, because now that we have open data, there are still challenges to challenge. The first is how you access the data. The second is what is the format. Finally, is there a standard? And well, what about data correctness? So let's check some of them. If you are a web developer, if you are a developer, probably when I tell you about accessing data, you probably think about using a web service. It can be a SOAP web service if you are an old guy like me. It can be a REST web service if you are younger and you prefer hype stuff. But in general, the problem is open data is just downloading a file, which defeats the purpose of what we are trying to achieve, to have like stream processing. Second issue is the format. Open data, you think means open format. Well, it might be the case, it might be not. It can happen that you need to download the PDF, and if you have ever needed to scrape data out of PDF, you know it's not a fun thing to do. And sometimes you need to download the Microsoft file. And I'm not talking about the new Microsoft files format, which actually are open source, I believe. But about the old ones, which are binaries and they are completely proprietary, also not fun. Third challenge is the standard. So I'm an old guy, I prefer XML because in general, XML allows you to reference a grammar. So in general, it's either a GTD, like that's really, really old, or an XML schema. That's the benefit of XML. And because you can reference a standard, but you might know about this comic that there are 14 competing standards, and then comes somebody who says, "Oh, I will create a standard like to have all of them reunited under the same standard, but then there are 15 competing standards afterwards. And that's the problem with, if you receive XML, I would expect to have XML schema, which is rarely the case. And finally, the last issue is data correctness. You might know about this saying that data scientists, they are complaining that 80% of their time they are not doing data science, they are curating the data that they receive. Well, if you are a data engineer, it's exactly the same stuff. So this is taken from the demo. The second and third columns are actually times, as you can see. And please let me know if you can understand what 25 o'clock means. I have no idea. It could be like 1 o'clock the next day. It could be 1 o'clock the exact same day, or it could be let's forget about it because actually it doesn't make any sense. We cannot infer what it means. So that's the kind of curation that you need to deal with when you deal with real world data. Now I need like a specification, I need a standard regarding public transportation, and there is something called the GTFS. The not so good stuff is I would expect a standard to be like coming from administration. In that case, it's coming from Google, but it's still open source. It's an open standard. And it's based on two kinds of data. The first one is you've got static data, and it's not really static. It's, let's say, data that doesn't change that often. For example, the stops. So if we are talking about public transportation, the stops of the bus, they are not changing every so often. And the train stations, even less. And there is dynamic data. And of course, the position of the transportation, they are very dynamic. So those are two legs of the GTFS that we need to cope with. And here is a table of all the files of the static data. I won't go through all of them, but as you can see, some of them are required if you want to implement GTFS. Some of them are optional. There is another one. This is a kind of stuff that you need to deal with. And then there is the dynamic model. And I did a UML diagram of it. And here this is the root message. And you receive like a lot of feed entities. And for each feed entity, you might receive the position of the vehicle. And yeah, I mean, that looks super simple. You've got the position of the vehicle. The job is done. So now we need to get our nails dirty and to implement it. So I work in Switzerland, so I checked about Swiss public transportation, and there is this Swiss public transport GTFS provider. So it's open data. I can use it freely and lawfully, and I can download. So weekly they publish these static data files, and then there is, for the dynamic data part, there is a REST endpoint. So it looks like a developer's dream. I just need to implement it. And that's what I did. And when I received the dynamic data, then I checked the vehicle position, and there was no vehicle position at all. That's because it's optional. And after thinking about it, I thought that you can only receive the vehicle data if the vehicle is as a GPS chip and can tell you its position precisely, which is not the case. It would be a bit harsh regarding the freedom and all that privacy stuff. So what they do instead is they send you stop time updates regarding departure and arrival. And that means that they published the planned schedule. On this stop number 1, I will be there at this time, and at stop number 2, I will be there at this time. And with the dynamic data, they tell you, oh, on stop number 1, I will be early by 1 minute. On stop number 2, I will be late by 2 minutes. And now we can see the benefits of stream processing, because if you already have the exact position, you don't need to actually process anything. You've got the position, it's done. Now we must do some computation. and we need to do some stream processing. And that's actually what we are doing. So what I will be like reading from the web service. And then because I have this huge XML envelope, I need to split it first, so that my first step in the data pipeline, I will split this one event into like multiple small events. And then I will do some enrichment, because in what I receive, I only have the reference ID. The full data is available in the static data files. So I will enrich it with the trip data, then the stop times data. My front-end developer asked me to transform everything into timestamps, so that's what I did. And then finally, I have the location data. And afterwards, I will push this into in-memory data grid of Hazelcast. So this is the architecture from a bird's eye view. I have a running Jet cluster, and in my demo, I only have one node because it wouldn't make sense to have multiple nodes. And I defined a first a pipeline. And this first pipeline is actually to load the static data files. So I will send it to the Hazelcast Jet cluster, and it will read from the different data files. Here I have only 2, but in the demo I have 5 or 6. And it will read them, and it will like store them in JSON format into the IMDG. And then that is done like before the demo. And during demo time, I will push another job to the cluster, and this job will actually call the REST endpoints, do all the joins that are necessary with the data that is already in Hazelcast IMDG, and push the full, complete, self-sustained events into Hazelcast IMDG on another map. And finally, on the front end, I will have a web application that will register to changes. So every time there is a push to this map, I will get notified about it, and then I will push it down toward a queue on a WebSocket, and my JavaScript frontend will be aware of that. That's already a lot. And well, I've talked a lot, and now perhaps it's time to show you the code. So I have 10 minutes left. So here I already preloaded the whole static data files, because it takes a bit of time and I don't want you to wait during that time. So now I should call the web service. So I will be streaming the data. And now normally I should start executing. So now I'm reading from the web service. The final step is to start the web application. And now, normally, I should have something. And now it's always the same. Perhaps nothing happens, so I will refresh it. And sometimes it happens because I need to open a new window. So let's try if, no, it works. It just took a bit of time. I'm always a bit stressed about it. So here you can see the bus lines in red, the train lines in red. You can see the green lines, they are buses, and you can see the position. And because I cannot follow exactly the position, I don't have the GPS position, I do some interpolations. So I know that at this time, the train, it takes a bit of time to move the stuff around because there is a lot of stuff in memory, and my computer is just a simple laptop. Now it disappeared, not great. Probably a display glitch. But here you can see it's moving. So I know that at this stop it was at this time, and I know that it's planned to be at the other stop at this time. So I'm doing some string some interpolation. You can also see that because I only have the longitude and latitude of 2 different stops, I'm drawing a line, whereas, well, it's Switzerland, so it's not flat line. I'm not really following the railroad or the road, but it still can give you a pretty good idea And this is the like the position of all public transportation in Switzerland. And of course, the more I read, the more I get. And so if I wait a bit, I will have everything at once. So this is the kind of stuff that you can achieve when you are doing stream processing. I will just stop the demo now because it's, as I mentioned, it's taking a lot of computer power and it's not that great. And here you can read the code, and I believe it's pretty self-explanatory, and it maps the previous slide that I showed you. I read from the web service, I explode the payload into multiple different JSON file, then I enrich it with the trips data, then I enrich it with the stop times, then I like change the hours to timestamp, and I enrich it with the stops. Here I just write it down in the log because I want to make sure that it works. And then because I want to like store it in a map, I need to like create a key value pair. So I just like get the ID, put it as a key, and the rest as JSON as the value. And yeah, that's what I wanted to show you. Like streaming, I believe, has a lot of benefits compared to the old batching model. If you've got available data, you can leverage it. And yeah, you don't need to work inside of company. If you are a developer, you want to play with it, you have open data to play with, you have a lot of untapped potential. And because you can, I believe, get very cool stuff down. So thanks a lot for your attention. You can follow my blog. You can follow me on Twitter. You can read the documentation of Jet if it got you interested. Of course, the demo that I showed you, everything is on GitHub. So I believe the README is quite complete. You are welcome to like ping me if you have questions about it. You can like run it at home. And if you are interested in more interaction, either you can ask me DMs on my Twitter account. They are open, or you can join our Slack channel. And now I'm done. So I believe there are some questions on Slidos. So let me check my phone. And I hope that I will get the questions. I will refresh. And I see, yes, I see something. In which industry do you see data streaming principle as the most needed right now? That's a good question. I don't know in which industry they are the most needed. I can tell you that, for example, in financial services, they are used a lot. Like our poster child for Jet is actually like fraud detection. When you insert your credit card into your terminal, well, as a bank or as a financial service provider, you want to give the answer as fast as possible, whether it's accepted or not. And in that case, if you would need to check a lot of different SQL databases, it wouldn't work that well. So what's the financial service provider, what they are doing, they are doing everything in memory, and then they run the transaction through a Jet pipeline, or at least a stream processing pipeline. And they check, for example, that, hey, the latest transaction was done in Hong Kong 2 hours ago, and now you're in New York, and probably there is an issue, or if everything is fine, then yeah, it's accepted. And because everything is in memory, it's processed very, very fast. And well, you as a customer gets the answer fast as well. So I hope I answered your question. What is the most efficient way to ensure there are no late events, that every event produced before some point in time was actually delivered? That's a really good question. So the issue with stream processing is, yeah, as I mentioned, you probably want to have some windows of time, and there is a difference between the timestamp where the event was produced and the time when you receive it. And it can happen that you receive the events in a different order in which they were produced. So that's the first problem. For that, we handle that with watermark. But then if you want to say, hey, I want like 5 minutes of like whatever, and some events is late, well, it's a design decision. It's up to you to decide whether how long you will wait for late events to arrive. And after some point, you need to decide, okay, after like 2 seconds or 5 seconds or whatever, late events, they don't make sense anymore. I will just discard them. And it's a design decision. Like everything, like caching or everything is just a trade-off. It depends whether you want to have like correct data, 100% correct data, or to have data that is very, very fast. Like the more you wait, the late the data will come, the late the results you will get, and the later the results you get, and the less interesting the data will be to you. So it's a design decision. It's a trade-off. It's only in your context that you can decide whether you put the cursor toward more correct data or faster data. Would it be better to go for NoSQL databases if you want to show many different data in a web application? Well, that's that's a bit outside the scope of this talk. It depends. I'm not. I mean, you know, this stuff about NoSQLs meant before it meant no SQL at all, and afterwards it meant not only SQL, and now it means no comma SQL. Like a lot of what you are doing with data right now, probably you don't need that much horizontal scalability in most contexts. I'm not saying never, but most of the stuff can be done with traditional like SQL databases. Right now, there is a consolidation between like NoSQL databases, like moving toward more transactionality, and of course being slower because of that, and SQL databases moving toward like more distributed ways of running, and of course losing a bit of consistency and having eventual consistency. So it's an interesting period. I wouldn't say that you should go for NoSQL databases, or like you can have a lot of different data sources and aggregate everything into IMDG, for example, or if you want to do stream processing, Jet, and have the same results. So you can keep your like traditional legacy databases and still have the same data aggregation capabilities. And I believe those are all the questions that I got. So if you've got more questions, now is the good time. If you are shy and you don't want to show up your name on Slido, as I mentioned, you can contact me directly on Twitter or join our Slack channel. Or perhaps if you want to join me just now, there will be this Ask Me Anything corner. So thanks a lot for your attention, and I wish you a good day and a good rest of the conference.